Hi, it's Kamgal. Today we're going to discuss formal charge and differentiate it from Octet Rule since the two often get confused. Later on, I'm going to give you my very own formula for calculating formal charge, so stay tuned. Formal charge is cool because it can tell you relatively how much electron density an atom has. For instance, if an atom is negatively charged, it has excess electron density, as in example number 2. Whereas, if an atom is positively charged, it has less electron density, as in example number 3. I know it might sound funny because we're so used to thinking that plus means more, but it's kind of the other way around here. An atom with a formal charge of 0 indicates a certain stability, in that the atom has no excess or lack of electron density with respect to its valence electrons. Let's see what we mean by that. So let's calculate the formal charge for each of the carbons I have highlighted in red. And the formula that we're going to be using is formal charge, or FC for short, is going to be equal to valence electrons minus surrounding electrons. And I just abbreviated each of those to make it easier. So we're going to go ahead and calculate the formal charge for each of the elements in red. So for the first example, we have formal charge is equal to valence electrons minus surrounding electrons. And we know that carbon has 4 valence electrons, so we draw in that number 4. Surrounding carbon right now, we have 1, 2, 3, 4 surrounding electrons. And I know what you might be thinking. Isn't each bond composed of 2 electrons? And you're right, each bond is composed of 2 electrons, one from carbon and one from hydrogen. However, we are looking solely at the electrons that are surrounding the carbon. Therefore, surrounding carbon right now is 4 electrons. So now we can go ahead and fill that in. 4 minus 4 is going to be equal to 0. Therefore, this carbon has a formal charge of 0. We can also say that it has no formal charge, so you'll probably see it without any charge. This carbon has no excess electron density and no less electron density because it usually has 4 valence electrons and surrounding it right now is 4. So that indicates a certain stability for that carbon. Now what about example 2? Formal charge is equal to valence electrons minus surrounding electrons. So we know that carbon has 4 valence electrons, right? So the first part of the formula is going to depend on the atom that you have. In this case, it's carbon, so it's always going to be 4. And surrounding carbon right now, we have 1 from each bond, 1, 2, 3. And we also have a lone pair. So that lone pair consists of 2 electrons. We have 5 surrounding electrons here. And 4 minus 5 is a negative 1 charge. Therefore, this carbon has a negative charge. And now you can begin to understand why a negative charge indicates excess electron density. Because carbon typically has 4 valence electrons, but surrounding it right now is 5. Therefore, a negative charge means that you have excess electron density. We tend to call negatively charged atoms anions, and specifically when they are carbon atoms, we call them carb anions. So we can draw in our formula, and now we can go ahead and we know that 4 valence electrons are always, but surrounding it right now, we see that there's 1 from each bond. 1, 2, 3. And there's no lone pairs here, so there are only 3 surrounding electrons. So the quick tip here is we count each bond once. So we see that there is a 4 minus 3 charge. We see that there is a charge of 1 or positive 1. Now you can begin to understand that a positive charge means you are lacking electron density. And why is that? It's because you have 4 valence electrons typically surrounding carbon, but in this example, you only have 3 surrounding it. So a positive charge means that you are lacking in electron density. And we tend to call positively charged atoms a cation. Please do not say cation because that is incorrect. And so a carbocation is a carbon that is positively charged. So let's go ahead and practice calculating the formal charge for multiple atoms within each compound. I numbered each of these elements so we don't get confused. So let's go ahead and draw in our formula. Formal charge is equal to valence electrons minus surrounding electrons. I'm going to go ahead and calculate it for oxygen number 1. Oxygen has how many valence electrons? It has 6 valence electrons, and that's never going to change for oxygen, right? So now surrounding oxygen, how many electrons do we have? Well, we have 1 bond here, so that indicates that we have 1 electron surrounding it from the bond. And now we have 3 lone pairs. So each lone pair gives rise to 2 electrons that's surrounding the oxygen. So we have 1, 2, 3, 4, 5, 6. Plus the 1 that we had from the bond, so we have 7 surrounding electrons for oxygen right now. So 6 minus 7 is going to be a -1 charge. So technically this oxygen here has a -1 charge. Let's go ahead and calculate it for oxygen number 2. So we know that oxygen has 6 valence electrons. And surrounding it right now, it has 1 from each bond. So this is a double bond, right? So we count each bond as 1 electron surrounding it. And so now we have 2 lone pairs, which give rise to 4 additional surrounding electrons. 1, 2, 3, 4. So in total, we have 1, 2, 3, 4, 5, 6. So we technically have 6 surrounding electrons right now. So 6 minus 6 is 0, therefore that oxygen atom has a formal charge of 0. So we don't write 0 here, we just don't write anything. That indicates that its formal charge is 0. Now let's go ahead and try the next examples. So I'll go ahead and write in the formula, formal charge of oxygen number 1. So we'll go ahead and say that oxygen has 6 valence electrons. There is 1 from the bond, and there are 3 lone pairs giving rise to 6 additional surrounding electrons. So there is 1, 2, 3, 4, 5, 6, 7. We have 7 surrounding electrons here. So now the formal charge of that oxygen atom is going to be a -1. So here in this nitro group, we have a negative charge on the oxygen atom. Let's calculate the formal charge of that nitrogen atom. And I just numbered them for correspondence, so don't freak out about the little subscripts there. So we know that nitrogen has 5 valence electrons. And surrounding it right now, we can calculate how many it has. 1, 2, 3, 4, 5. Right? We have 3, 1 from each bond, and then we have 2 from the lone pair. Therefore, surrounding it right now, there are 5 surrounding electrons. So 5 minus 5 is going to be 0. Therefore, this nitrogen has a formal charge of 0. What about that third element, the oxygen atom? So that oxygen atom, we know that it has 6 valence electrons, right? Oxygen has 6 valence electrons. And so we have 1 from each bond, and then 1 from each of these surrounding electrons here. And so we have a total of 6 surrounding electrons. So 6 minus 6 is 0, and therefore that oxygen element has a formal charge of 0. Now let's take a look at the third example. We can go ahead and calculate the formal charge here of oxygen. So that oxygen element has 6 valence electrons, we know. So it has 1 from each bond, and it has a lone pair. So we count that lone pair as 2 electrons. So now surrounding it, it has 1, 2, 3, 4, 5 electrons. And we can see here that it's already drawn in for you. I should not have drawn it in, but 6 minus 5 is going to be a +1 charge, right? And this is the hydronium ion. Don't worry about naming too much. It's just going to be helpful for you if you start to recognize that this is hydronium, H3O+, and whatnot. We can even go ahead and calculate that formal charge of hydrogen for fun. Each hydrogen here is the same, so we'll just pick one. So we know that hydrogen has 1 valence electron. And surrounding it right now in this element is 1 from this bond, right? We count each bond as 1. So technically it has 1 surrounding electron. And 1 minus 1 gives rise to a formal charge of 0. So you see that hydrogen here has a formal charge of 0. Now let's go ahead and take a look at these examples. We're going to determine the formal charge of each of these atoms. So for this example, let's take a look at the bromine. Formal charge is equal to valence electrons minus surrounding electrons, and so we see that bromine is a halogen, and you should know that halogens always have 7 valence electrons. And surrounding it right now, we see that there are 1, 2, 3, 4, 5, 6, 7, 8, right? There are 4 lone pairs, therefore there are 8 surrounding electrons. So surrounding it right now are 8 electrons, and therefore this has a charge of -1. So this is a negatively charged bromide ion. What about example number 2? We can go ahead and calculate it for the oxygen. So the oxygen here has 6 valence electrons, and surrounding it right now, it has 1, 2, 3, 4, 5, 6, and 1 from the bond. So that is 7 surrounding electrons. 6 minus 7 is -1, and therefore this oxygen has a -1 charge. Let's go ahead and calculate it for the nitrogen atom. So this nitrogen atom has 5 valence electrons. And surrounding it right now, there's 1, 2, 3, 4, 5, 6, right? There are 2 bonds and 2 lone pairs. So 5 minus 6 is actually going to be -1, and therefore you're going to have a -1 charge on that nitrogen. Let's go ahead and do the next one. So we know that oxygen number 1 here is going to have 6 valence electrons, and surrounding it right now, it has 1, 2 lone pairs and 1, 2, 3 from the bonds. So therefore it has 5 surrounding electrons. So therefore this oxygen actually has a charge of +1. Now what about the carbon element? So the formal charge of the carbon, element number 2 here, we know that carbon has 4 valence electrons, and surrounding it right now there is 1 from each bond, so there are 4 surrounding electrons. And therefore that element has a formal charge of 0. And I just need some more room. So now the formal charge for the third element of the oxygen is going to be 6 valence electrons minus, surrounding it right now is 1, 2, 3, 4, 5, 6, 7. Therefore, there are 7 surrounding electrons. And therefore, that makes that a -1 charge. And that is a CO2 group. So now we can go ahead and do the next one. So for the next one, we have a formal charge for bromine. So let's go ahead and calculate bromine's formal charge. So we know that halogens have 7 valence electrons. And surrounding that bromine atom right now, there are 1 from each bond. So don't forget that this is technically 2 bonds attached to bromine. So bromine is contributing 1 electron to this bond and 1 electron to that bond. And so technically there are 2 electrons, 1 from each bond, and then 1 from each of those electrons in the lone pair groups. So that is going to be 6 surrounding electrons. So 7 minus 6 is going to be +1. So that is going to be a positively charged bromine. And later on, you're going to learn that this is actually called a bridged bromonium ion. And you're going to see what cool things that will do. And we could even calculate the formal charge for one of these carbon groups. So the formal charge for that carbon group, we know that carbon has valence electrons of 4. And now you also see that it's bonded to 2 hydrogens. And we can draw them in ourselves. So let's go ahead and calculate that. So we know that surrounding it right now, there are 1 from this bond, 1 from this bond, and technically this carbon atom has 2 bonds here, right? So technically it's contributing 1 electron to this bond, 1 to this bond, and 1 to this bond, and 1 to this bond. And therefore surrounding this carbon atom right now is 4 surrounding electrons. So technically this atom has 4 minus 4, which is 0. So technically this carbon has a 0 formal charge. And this carbon is technically the same as this carbon, right? They have the same chemical environment. It's just that I decided to draw out the hydrogens in this example. Nonetheless, they both have a formal charge of 0, since they both have the same chemical environment. Now let's go ahead and calculate it for the last example. So we can calculate our formal charge is going to be for bromine here. And we can see that bromine has 7 valence electrons, and surrounding it right now, we know there are 1, 2, 3, 4, 5, 6, 7 surrounding electrons, right? 1 from the bond, and then 2 from each lone pair. So 7 minus 7 is going to be a formal charge of 0. So technically this bromine has a formal charge of 0. Now let's take a moment to discuss octet rule, because I know when I was a student, I would often confuse it with formal charge. Octet rule states that an element tends to have 8 surrounding electrons and usually cannot have more than 8. And I say usually because there are exceptions to this, such as with sulfur and with phosphorus. And we're going to explain why in a little bit. But for now, let's take a look at some examples. So if we look at the first example with bromine, we see that surrounding bromine, there are 8 electrons. And therefore, bromine is obeying the octet rule while incurring a formal charge. So bromine is good to go. So now with hydroxide, we see that there are 1, 2, 3, 4, 5, 6 surrounding electrons, and we see that there is a bond. Now here's what gets confusing for students. With octet rule, we count each bond as 2 electrons, unlike with formal charge where we count it as 1. So here we see that surrounding the oxygen element, there are 8 surrounding electrons, and that's what allows oxygen to have that full octet and allows it to obey the octet rule. So oxygen is good to go. Now what about the nitrogen element? So you see that with the nitrogen element here, we have 1, 2, 3, 4 because of the 2 lone pairs. And now remember, we count each bond twice. So we see that there are 2 electrons in this bond and 2 electrons in this bond. And therefore we have a total of 2, 4, 6, 8. 8 surrounding electrons. And that's what allows nitrogen to have that full octet. So now we see that nitrogen is good to go. So now you might be wondering, why 8? Why are there 8 surrounding electrons? And that's because elements like to fill their outer shell, and that usually requires 8 surrounding electrons. And so once they fill that outer shell, they get this certain sense of stability. So they'll arrange themselves with other atoms so that they can fill that outer shell and obey the octet rule. So now let's take a look at some of the weird examples we have below. So if we take a look at this carbon element, we see that it has 1, 2, 3, 4, 5, 6 electrons here and 2 electrons here, and that makes for a total of 8 surrounding electrons. So this carbon atom is good to go. Now what about the oxygen atom surrounding it over here? We see here that this oxygen atom has 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen atom also has 8 surrounding electrons. This oxygen atom is good to go. And now we can take a look at the last element here. So we have 1, 2, 3, 4, 5, 6, 7, 8. And on to the next example. So we see here that this bromine element has 2 bonds. And remember, we said that we count each bond twice. So there's 2 electrons in this bond and 2 electrons in this bond. And we also have 2 lone pairs that give rise to 4 surrounding electrons here. Therefore, we have a total of 8 surrounding electrons. And this bromine element, as funky as it looks, is good to go. So for this last example, we have bromine here. And remember, we said that each bond consists of 2 electrons, and therefore there are 6 additional electrons from the lone pairs for a total of 8 surrounding electrons. And therefore, this bromine atom is good to go. So this was just some practice differentiating octet rule with formal charge. So that's it for this video. If you liked it, please leave a thumbs up and feel free to subscribe. Happy studying!